Hey everyone, I'm Praveen and welcome to AI Sparks, where artificial intelligence meets innovation and excitement. On this channel, we spark curiosity and ignite imagination with AI powered insights, tutorials, and explorations. From machine learning to robotics, we'll dive into the future today. Imagine a student solving math problems, getting some right, some wrong. But instead of just checking the final answer, they pause. They ask, where exactly did my thinking go off track? That's the heart of this paper. Internalizing meta experience into memory for guided reinforcement learning in large language models by Shaiting Huang and Zeicheng Li along with their team at USTC. And today we are diving into how they teach language models to not just learn from rewards but to learn from their own mistakes. Let's start with the problem. Reinforcement learning with verifiable rewards RLVR has been powerful. It checks whether the final answer is correct. Reward equals 1. Wrong. Reward equals 0. But here's the issue. It only judges the outcome. It doesn't understand why the reasoning failed. Humans don't learn like that. We practice, we verify, then we reflect. Standard RLVR misses that reflection step. The authors call this missing piece meta experience, reusable knowledge distilled from past errors. So, what is their solution? They propose meta experience learning MEL. Here's how it works. First, the model generates multiple reasoning trajectories using GRPO. Some are correct, some are wrong. Then comes the magic. MEL pairs a correct and incorrect solution and asks the model to locate the bifurcation point, the exact reasoning step where things went wrong. From there, it performs deep diagnosis. What assumption failed? What constraint was ignored? Then it abstracts that into a general heuristic. Not 2r sin a over 2 is wrong, but something like if applying a formula verify that the angle matches the geometric meaning, that's meta experience. But here's something clever. They don't trust every extracted heuristic, they validate it through replay. They inject the meta experience back into the prompt, ask the model to solve the problem again, and only keep the experience if it now produces the correct answer. That filters hallucinated insights. Now comes internalization. Instead of storing these as external memory, they fine tune the model using negative log likelihood on the verified meta experiences. In other words, the model learns to predict its own reflective insights. This creates a dense process level reward signal, almost like a language model process reward, and the final objective becomes RLVR reward plus meta experience return. Trajectory level learning and knowledge level learning optimized together. So does it work? Yes, consistently. Across Quen 3, 4B, 8B, and 14B models, on benchmarks like AMC 23, Math 1500, Olympiad Bench, MEL improves pass at 1 by roughly 4%. But more interestingly, training curves show faster early learning because meta experience acts as dense guidance when rewards are sparse and scaling helps. Larger models generate higher quality meta experiences. Retention ratio increases with size. There's also a qualitative example. In a geometry problem, the baseline jumps straight into calculation. MEL pauses, outlines the theorem, checks angle consistency. It develops what the authors call bitter lessons, internal safeguards. In the end, MEL transforms failure into structured cognitive assets. It's not just learning to be correct, it's learning how to think about thinking. And that might be the next frontier of reinforcement learning for LLMs. If you found this helpful, hit like, subscribe, and comment which AI system you want to build next. Stay sparked. See you in the next video.